And I think, if I'm not mistaken, both of them were for his contributions to, verification techniques. Professor Vardi is also a frequent visitor to India, so many of us would also know him that way. He used to come for FSTTCS, the conference many years back, and he's also visited IIT Bombay more recently. Okay, so it's a pleasure to have you, Professor Moshe, and today Professor Vardi will be telling us about machine learning and logic. Okay, and he's probably the best person to tell us because he's well versed with both logic and machine learning. So over to you, Moshe.
Namaste. Thank you for the very kind introduction, and thank you for the opportunity to address you this evening. Let me just go to, no, something happened here. Okay. Something happened with my screen. Excuse me, I'll have to stop sharing. Okay, I'll have to reshare. Sorry about that. Open share tray.
So maybe while Moshe's sharing, if there are questions, I'll put them on the chat, any kind of clarification questions, or just go ahead and ask them. And if there are major discussion points, we could do that at the end of the talk.
Okay, okay, let's go again. Share. Stop sharing, resharing. Okay, do you have full screen mode now?
Yes, Professor. Okay.
Okay, excellent. Okay, so I will talk about machine learning and logic, and I'll talk about fast and slow thinking, which I'll explain in a few minutes. So there is a sense of the last few years that computer science is changing in a fundamental way, what some people call paradigm shift. We hear every day now about machine learning and big data and ChatGPT and Bard and Bing and what have you. And the sense is that something fundamental has changed. In I think it was 1960, Thomas Kuhn wrote a famous book, The Structure of Scientific Revolution. And he introduced the phrase paradigm shift. And his argument was that sometimes science goes through such paradigm shift. The most famous one, for example, when we went from Ptolemaic astronomy to the Copernican astronomy, putting the sun at the center of the solar system. And when you think about paradigm shift, you think, okay, we throw away the old paradigm. Nobody does Ptolemaic astronomy anymore. We all do today Copernican or even more elaborate Newtonian astronomy. So you throw out the old, you bring in the new. But if you talk to philosophers of science, they say this was somewhat simplistic. In reality, scientific theories refine old ones. They don't replace them. Take, for example, we have general relativity. So does it mean that we are done with Newtonian mechanics? Absolutely not. Your house is built on the basis of Newtonian mechanics. We went to the moon with Newtonian mechanics. General relativistic effects get into consideration much later. So my thesis is that I will try to work here is the data science refine formal science. By formal science, I mean computer science was very often based on formal model. For example, in verification was formal model of the system, formal specification. So data science refine formal science, it does not replace it. We have to be able to combine them. And the metaphor I want to use is of fast and slow thinking. And that term was popularized by Daniel Kahneman, a very well-known psychologist, received the Nobel Prize in economics for behavioral economics. He wrote a book in 2011, Thinking Fast and Slow. And his argument that really human intelligence consists of two different types of intelligence. One is pattern recognition, essentially. This is fast thinking. You drive and you see a sign and you have to think clearly, what is this? Is this a stop sign or not? This evolutionary came from, think about it. You're walking in the savannah high grass, you see something yellow moving in the grass. And you have to quickly think, is this a lion or not? If it's a lion, I need to get out of here. But there's also slow thinking where that's capacity of reasoning. For example, what do you do when you see a stop sign? It's a rule. You have a rule. When you see a stop sign, you have to stop. If you go back to your village and you say, I saw a lion out there, let's plan on how to hunt the lion, that requires slow thinking. So machine learning is just about pattern. Logic is about semantics, about the meaning. And this is part of the issue that we're hearing now about, for example, about ChatGPT. Yes, it talks very fluently, but does it understand what it is saying? And a good example of this duality between fast and slow thinking was highlighted by a paper by Amnon Shashua in 2017. So Shashua was a professor of machine vision in Israel, and he started a company called Mobileye, which Intel bought for billions of dollars. And because everybody thinks that machine vision will be important to autonomous driving. In the 2017 paper, he argued there's no way we can get to the desired level of safety for autonomous vehicle merely by training the vehicles on actual roads. And his argument was that he thinks that that autonomous vehicle AVs have to be 1,000 times safer than human-driven vehicle because we are very tolerant of human error and we are very intolerant of machine error. In the United States, we have about, I think, somewhere around 50,000 people get killed every year in car accident, and we just accept it. But suppose you reduce it by a factor of 10, that would still mean that every week you'll have about 100 people will get killed in car crashes. He said the public will not tolerate it. So we have to make it the car much safer. And he said that if we do going to be data driven, we'll have to test drive about 1 billion miles. It's just not feasible. So we have to combine data, test driving, 1 million miles is doable, but with reasoning, with models. So to me, the grand challenge today is how to take these two approaches to AI. One is symbolic AI, logic, and the other one is machine learning. How do we combine it together? And that's what I will be trying to talk about. Another argument for why we need this combination of logic and machine learning has to do with automated decision systems. So automated decision systems are getting deployed more and more. You know, you go and you ask, for example, you apply for a loan, and the decision may be made by a machine. In 2018, James Lawrence and Chris Hankin wrote in CSEM about regulating ADS, automated decision system. And they wrote the widespread adoption of AD system will be economically disruptive and will raise new and complex societal questions. Disdain for regulation, they wrote, is pervasive to tech industry. In the case of automated decision making, this attitude is mistaken. Now, of course, we have not yet figured out completely how to regulate automated decision system. People talk about faith, fairness, accountability, transparency, explainability. Now, if you think about explainability, for example, it has to be in a human level explainability. You cannot say the explanation cannot be this neuron fired and then this neuron fired. That's not an explanation. If you ask me why, suppose I write a recommendation letter and I recommend someone up for promotion, I can't just say, well, a particular neuron in my brain fired. That's not an explanation. I have to offer a symbolic explanation, and that's why we need logic. So if we want to be human-centered AI, then we have to offer explanation in a high level. And it's interesting, I can quote a well-known mathematician, Hermann Weyl. This is a typo, excuse me, it should be 1895, late 19th century, but he was active in the first half of the 20th century. And he wrote a beautiful quote: "We cannot deny that there lives in us a need for theory. This is absolutely inexplicable from a merely phenomenalist standpoint. You can't just point to the data. You have to offer high-level explanation. That need has a drive to create, directed to a symbolic layout of the transcendent, which demands satisfaction." So again, we need, if we want to have high-level human-centered AI, we need explainable AI, but the explanation has to be high level, not low level. So again, we have to combine logic with machine learning. And this is something many people today call neurosymbolic reasoning. And that's a large area. I cannot cover fully neurosymbolic reasoning. I will talk about my approach. And my approach is to make logic quantitative. So classical logic is about true and false. And the excluded middle, there's nothing, just true and false. And I will show you how I work to make logic quantitative. But I'll go back first to the middle of the 19th century. And you have an insight by George Boole that if you go back to the Aristotelian syllogism, and now we're talking about the 4th century BC, there are classes of objects. And the logical operation are operation about classes. So for example, conjunction is really an intersection. So if I have the class of white thing and the class of sheep and the class of white things, the intersection is white sheep. And not only its intersection, but we can view it as a product operation. And similarly, disjunction is a union of sets, and you can view it as a union operation, as addition operation. So Boole's argue that you can think about logic algebraically, and that's what ultimately gave rise to what we call Boolean algebras. So now we have algebraic treatment. So what Boole has done, he has taken logic, which for more than 2,000 years before him was always considered part of philosophy, and he treated it mathematically. So this is really the beginning of mathematical logic, the fact that we can think about logic algebraically. And one question that came out of Boole's work is what we call today, this is a more modern formulation, but the question really already arose in the 19th century, Boolean satisfiability. So if you're given a Boolean expression based on the, and you have Boolean variable that are either true or false, or 0 or 1, and you combine them using and, or, and not, can you satisfy this? Is there an assignment will make the whole expression a value to 1? So here we see an example, not x1 or x2 or x3, and not x2 or not x3 or not n x4 or x4, and x3 or x1 or x4. And you can easily see that if I make x1 and x2 0 and x3 and x4 1, the whole thing will evaluate to 1. But when you have four variables, you only have 2 to the 4, which is 16 possibilities. So that shouldn't be too hard to check 16 possibilities. But what happens if it's not 4 variables, but 40 variables? Then you have 2 to the 40 possibilities. Suppose it's 400 variables, 4,000 variables, maybe even 4 million variables. How would you solve a problem then? And this was a question that people start thinking already in the 19th century. William Stanley Gibbons, who was a follower of Boole's, I have given much attention, therefore, to lessening both the manual and mental labor of the process. And I shall describe several devices which may be adopted for saving trouble and risk of mistake. So he actually built a logic machine that can reason about, guess, 4 Boolean propositions. It was moving wooden pieces, so don't blame him if he couldn't scale it to something bigger than that. Shortly after him, Ernest Schroeder, a German algebraist and logician, amazing quote to me, getting a handle on the consequences of any premises in Boolean logic, or at least the fastest method for obtaining these consequences, seems to be the noblest, if not the ultimate goal of mathematics and logic. And this question was kind of left open for more than 100 years. How do we find the fastest method? And we still do not have a definitive answer, but at least about 50 years ago, it was established that Boolean satisfiability is NP-complete. So if it's in polynomial time, we know that NP equals NP. So this is some evidence for the hardness of Boolean satisfiability. But at the same time, people have tried to continue to work on solving Boolean satisfiability. And the first program that we know that has done it was already in 1955. So remember, the first computer, ENIAC, is 1946. Within less than a decade, people are writing a program to do Boolean reasoning. It was called logic theorist. In 1958, Davis and Putnam, and Davis just passed away just about a month ago, in his 90s. He was 94. But in 58, together with Putnam, he wrote a paper, Computational Methods in the Propositional Calculus. It was not published as a report at the National Security Agency in the United States. This is the agency that is responsible for signal intelligence. Then Davis and Putnam published another paper in 1960, Davis, Logman, and Loveland, another paper in 1962. And out of this came a method that we call today DPLL. So it really is a simple method. Convert the formula to conjunctive normal form. This is conjunctive normal form. It's a conjunction of these junctions, and negation is only applied to variables. Then you just do backtracking search. And there is one heuristic that if one of the disjunctions, suppose that we have made x2 and x3 false, then here we're left only with not x1. It means that x1 must be false to make it true. So there's no reason to branch anymore once you have what we call a unit clause. So by the early 90s, people could solve problems with typically hundreds of variables. And we told them, well, these are small problems for relative to industrial problems. They say, well, it's NP-complete. What do you expect? But something miraculous happened in the mid 90s, and people start to discover a whole bunch of new heuristics. And out of this came the method that is today the prevalent method is called CDCL, conflict-driven cross learning. And it's a combination of heuristic. I can spend a lot of time talking about just this heuristic. I'll just go very briefly over each line. One is back jumping. Backtracking, you go one level at a time. Back jumping, you try to be smarter, and when you can, you go several levels up at a time. Unit clause is important, but how to identify unit clause quickly, fast, requires a special data structure. Close learning means that when you reach a point in a search where you fail, you analyze your failure and you say, what caused this failure? And then you learn a new clause that would block this particular mistake that you made. So you're not going to make the same mistake again. You have to branch. Branching requires choosing which variable to branch on. People try to develop very, very smart branching heuristic, but they were slow. You can have very, very fast heuristic, but not very smart. The key is to find the right combination of speed and smartness. And this is the joke here is that Superman had enemies. One of them was Brainiac, that was smarter than Superman, and Speedemon was faster than Superman. But Superman won because he was the right combination of speed and smartness. And finally, restarts. Sometimes you just go up and down the search tree and you say, this is not going anywhere. So you just go to the beginning and you restart. But all the clauses that you learn, you use them in the new search. So the next search, you're going to be smarter. And in 1996, a tool came from University of Michigan, GRASP, 2001 SHAF, and that gave rise to today it's an active area and people can solve problems with millions of variables. A decade ago, a colleague of mine, Sajid Cheshire from Berkeley, wanted to get a sense of how much progress such solver has made in one decade, from 2000 to 2012. So he took a decade of such solvers, ran them on the same benchmark on the same machine. And he showed that a problem that took 800 seconds in 2000 was done in 1 second in the year 2012. So we had a 3 orders of magnitude improvement in over a decade. So some people really start calling it Moore's law for such solver. We're still making amazing progress. And the phenomena even attracted the attention of Don Knuth, the closest we have to patron saint in computer science. And in 2016, he received a recognition from the Society for Industrial and Applied Mathematics, and he gave the phenomenon lecture, and he dedicated to satisfiability. In fact, one of the sub-volume, they're called fascicles, of volume 4, the mythical volume 4 is now not one volume, but several sub-volume, and he dedicated it to satisfiability, Boolean satisfiability. And he wrote, the story of satisfiability is a tale of a triumph of software engineering. I would have called it algorithmic engineering, blended with rich dose of beautiful mathematics. And the progress has been so impressive that now such solving is an industrial reality. Microsoft has been in the forefront. Even a decade ago, they published a paper in CCM describing how Z3, the research solver, is being used in many aspects of software development, not in research, in software development, symbolic execution, model checking, static analysis, model-based design, and on and on. So as we speak today, Microsoft has hundreds of machines running such solvers. Now, my interest was in formal verification, and the motivation there was that hardware and software design, you look at developing system, it's a huge market. It's estimated at $1.5 trillion per year. And everybody who builds software or hardware system knows that the difficult part is we have something in mind. We have what's called intended functionality, designer intent. You build a system and it doesn't quite do what you intended it to do. You have to do functional verification, making sure that the system satisfies its intended functionality. And when people try to quantify at industrial software or hardware development, they tell you verification is something like 70 or 80% of the development effort. Coding is the easy part. Verifying is the hard part. Now, my own research for many years has been in formal verification. So there you construct a mathematical model of a system, and you say essentially prove a theorem about this mathematical model. And this has been a huge success, so to speak. I mean, you have several Turing Awards were given in computer science for formal verification. But when you go and talk to people in the industry and you say, okay, how much? You said you do formal verification. They say, of course. When you say how much, then the best way to do it is to say, okay, how many people do you have in your verification team working on formal verification? How many people work on non-formal verification? And then you get at most 10% work on formal verification. So what do the other 90% of the people do? They do what we call testing. You simulate the system under different testing scenarios. You check the result, whether you know what the correct results are supposed to be. You simulate the system, you test the system, you see whether it gives you the right result. So this is the dominant method still to this very day. As much as I'd like to celebrate the success of formal verification, the reality is most of verification is dynamic. So you take the design, you simulate it with input test vectors, and that's what they're called. And the test vector represent different verification scenarios. What happened in this case? What happened in that case? And you compare the result to the intended result. And if you find a discrepancy, it means you find an error, and then you have to analyze the error. Of course, the challenge is that the test space is exceedingly large. It's astronomically large. We cannot really hope to cover everything. Just as a simple example, one of the most famous hardware bug ever was in the mid-90s when the Pentium came out, and it turned out Pentium could not do floating point division correctly. It made a mistake, made mistakes. So suppose you have suppose we do floating point division of 128-bit floating point numbers. Suppose you say, you know what, why don't we try all of them? We'll always divide and then we'll multiply to see if we get back the correct result. It's 2 to the 256 possibilities. So even if you started at a big bang, you will not finish before the sun will go nova, and the whole solar system will be gone. So you cannot do that. These are humongous. These are people call them cosmological numbers. So it's not scalable. So instead, the method used to be that people do manual test generation. So you have a whole team of verifiers, verification engineers, and they sit down and they know a lot about problematic input areas. They read the documentation, they read the requirement, and they generate test cases. The problem is that writing tests is like writing code, and we know that a software developer can write about 20 lines per day. So they can write about 20 test cases per day. So even if you have 100 verification engineers, they can write 2,000 cases per day. So a good, especially today with hardware emulator will go through these 2,000 cases in a few seconds. So we need to be increase productivity. And a brilliant idea came in the mid-90s, was developed by three researchers, Lichtenstein, Malka, and Aaron at IBM Research Haifa. And the approach is called random consent test generation. So now the verification engineer does not write test vectors, write constraints that describe problematic input areas based on designer intuition, bug report, documentation, and the like. Write constraint. Each constraint is a scenario, set of constraints is a scenario. Now we write consent solver to solve the constraints, and the solution are used as test inputs. Now this requires that we can solve constraints, but today we have very good, like we have such solver that can actually solve large formulas. So this method has become today the dominant method in the hardware industry. You write constraints, you use a consent solver to generate test vectors. But we do not want our test vectors to depend on the internal of the solver, because we're looking for errors. If we don't know where the error is, our best chance is to look at random test vectors. Okay, if you go to a place and you have to choose to start searching, you have you're going to a movie theater, somebody has a bomb. What is you should go sequentially. You should start sampling at random to see who may have a bomb. So we need to sample randomly, but it's not enough to be random. You have to be uniform, because we don't know where the error is. We don't have an indication where the error is. So this gave rise to the problem that I heard first about it in 2006, which is called uniform generation of such solutions. You're given a Boolean formula, a SAT instance. You have a SAT solver, but you have to generate a random solution uniformly. And you have to scale to industrial size problems. So I heard about this problem first in 2006, and I remember talking to Steve Cook about it. Steve Cook is one of the fathers of complexity theory. He proved that satisfiability is NP-complete. And I told him about this problem. He said, oh, it's a beautiful problem. I have no idea how to address it. So it turns out this problem has many applications. One I just discussed, but many other applications. One of my favorite was people discovered it when they started developing MOOCs about a decade ago. So MOOCs are massive open online courses. And some of the early courses had like 100,000, they were so popular, they had 100,000 students. So they have to develop homework assignment for 100,000 students. But you cannot just have one problem set, because the students discuss everything on online forums. So you post one problem, somebody will post a solution, everybody has a solution. So you have to develop 100,000 different problems for each instances, for each problem. How do you do it? You parameterize the problem, and you generate, you get values for the parameter randomly. And this way the chance of people finding, yes, there could be some repetition with some probability, but people will have a very hard time finding if it's random. So the people have the same value parameter will not find each other. So it turned out that this problem was studied by theoreticians. When I start looking into it, it turns out that already in the 80s, people studied this problem, and they have come up with theoretical algorithms, and they continue to develop it. And then the best algorithm finally was published in 2000. And it was a randomized polynomial algorithm with an NP oracle. NP oracle you could use to the SAT solver. So in about a decade ago, together with a student, Kuldeep Mill, and a collaborator, Supratik Chakraborty from IIT Bombay, we decided to implement the Bellaire-Goldreich-Petrang algorithm, the BGP algorithm, which was, and we managed to scale it to 16 variables, but it wouldn't scale above it. And I remember that Kuldeep wanted to publish the paper, and I said, if we submit a paper for 16 variables, they're going to laugh at us, because people are solving already huge problem. 16 is nothing, it's a toy problem. So we start working harder, how to scale it up. And we look what else is available. And there are techniques based on BDDs, Boolean binary decision diagrams, or Boolean decision diagrams. And people have done it. That scale up to about 1,000 variables, still not good enough. If you want to go above it, people use Monte Carlo Markov chain techniques, and they give you much better scalability, but they sacrifice on uniformity. We did not want to sacrifice on uniformity. So they tell you when it comes to uniformity, it's best effort that we're doing. They gave you no guarantee on uniformity, and we found it unacceptable. So in the following few years, we developed a new algorithm called Unigen, together with some other collaborators, Daniel Fremont and Sanjit Cheshia. And we did sacrifice a little bit on uniformity. I'll show you in what way. But we got scalability. We used techniques that were already emerged, universal hashing, which I'll talk about, SAT solvers, SMT solver, I'll explain also. And now we can scale to millions of variables. And even after parallel processing, you can have several machines sampling at random. So we sacrifice a little bit on uniformity. So what do I mean by that? What is almost uniformity? So if you have a formula phi, the solution space is solo phi. We'll call it solo phi. Suppose a kappa solution. In uniform probability says that every satisfying assignment will be chosen with probability 1 over kappa. Well, that's a bit difficult. So we said, give me a parameter epsilon, and I will guarantee you that every solution y will be chosen with probability which is within a factor of 1 plus epsilon from above and below to this 1 over kappa. Okay, so if you want everything to be with probability 1 over millions, I'll be almost 1 over millions. I'll deviate from it maybe by 1% from 1 over million. So, and you choose how close you want to be. Of course, the smaller epsilon, the more effort you'll have more computational effort you'll have to invest. So the basic idea goes back to universal hashing. So let's see how we do it. We take the solution space and you divide it into roughly equal small cells of some small size. We'll see what it means, small size. Then we choose one cell at random. And then if the cells are small enough, I can enumerate all the solution in that cell. And then I'll choose one of them at random. Now, because the cells are not exactly equal, it's not exactly uniform, but I can make it almost uniform. But the question is, how do we partition? This is a crazy solution space. We know nothing about the solution space. It's very complex. How do we divide it into roughly equal small cells without knowing the distribution of the solution? And here we use the magic of universal hashing, which idea that was developed in the late 70s, early 80s. So in general hashing, you have a large space, 0, 1 to the n from some large n, and you map it to a small space, 0, 1 to the m for some small n. For example, you want to take you have a space of maybe password can be up to 100 characters long, but you can't store it in a table of all possible passwords, so you store it in a much smaller table, hash table. Now, a good hash functions would tell you that if the input was distributed randomly, then the output, which are the cells, will also be roughly equal in expectation. But that required that the input be nicely distributed. But for example, when it comes to passwords, we know they're not uniformly distributed. When it comes to SATs, as the solution paid for a SAT problem, we have no idea about the distribution of the solution space. So universal hashing says, no, you don't have the input to be random. Instead, you have a family of hash function, and you'll choose a hash function randomly from that family. And now the beautiful result is that if you have arbitrary distribution, but you randomize in choosing the hash function, then the output space will be uniform in distribution. All the cells will be roughly equal in distribution. In expectation. So we get almost equal cells. So this is the magic of universal family of hash functions. Now we require another property, which is a bit technical, but you'll see why it is important. It's not enough that each input is hashed uniformly. I want to reason about collisions. And that means that I need different inputs to be hashed independently. Just uniformity does not guarantee independence. So the theory of universal hash function talk about R universality hash, a family HNMR, We have the two parameters we already saw, n and m, the size of the input space, the size of the output space. R is the degree of universality, and R universal means that every R elements are mapped independently. The higher the R, the more universality you have, and that gives us a guarantee on the distribution of the sizes of the cells. If you want high universality, in the BGP algorithm, use polynomial of degree R minus 1. So if you wanted higher R, it means polynomial of higher degree. And that had impact on complexity. So the higher universality, the higher complexity. So BGP went all the way to n universality, and they got to guarantee that all cells are small, and from that they got uniform generation. We showed that 3 universality is enough to tell us that each cell is small with a high probability. That gave us almost uniformity. And that was really this step going from n universality to 3 universality enabled us to scale from tens of variables to millions of variables. But that's not enough. We need another technology to solve our problem. So what I say hashing, but you say what does it look like? How do I hash the space of truth assignments? So we want to partition 0, 1 to the m into 2 to the m cells. Suppose we have variables x1 to x2 to xn. Create XOR constraints, XOR equations. Each XOR equation is an equation like you see here, and you can think of it as the plus as XOR. So it's an equation modulo 2 of the Boolean variable. Each variable is chosen with probability half. Probability half it's in, probability half it's out. And then the value is also chosen, the 0 or 1 probability half. So you can think of each such XOR equation, it splits the solution space in half, not in a geometric way, in kind of a crazy way. But if I have m such XOR equations, I'll have 2 to the m cells. But now each cell is a conjunction of CNF and XOR clauses. If I want to enumerate the solutions inside the cell, I have to solve this combination of CNF and XOR. How do I do that? So after the explosion of new ideas in the mid-90s and early 2000s of SAS solving, people say, can we use SAS solving to generate richer problem domains? For example, can we deal with linear constraints? So this became known as SMT solving, SMT satisfiability modular theory. So it's not just Boolean constraints, but you have richer constraints. And this also has been tremendous progress since 2000. And in 2009, Mateus developed a specialized solver for combination of CNF and XORs. Now his goal was to, and he showed how you can be smart and combine SAS solving with Gaussian elimination. Because when you have linear equations modulo 2, you can solve them using Gaussian elimination modulo 2. So we can solve such equation, but the combination is difficult. And he showed how to combine the two techniques in a smart way. His goal was to call it crypto minisat because he was hoping to break cryptographic protocol. That was not a success. But in one of the miracles of science, his solver was waiting for us to use it for our problem, which was very far from what he had in mind. And that enabled us to build Unigen. So Unigen was based on this universal hashing and SMT solving. So one is we wanted to compare the uniformity. We want to evaluate the uniformity of Unigen. I mean, it's almost uniform. So we said, okay, we want to be within, so we do the comparison. We took a problem that had about 16,000 solutions. And we sample because then we can just enumerate them and sample uniformly, really uniformly. And then we look at then you count each solution, how many times it comes out in the sampling. And you compare the two, you get bell curve, which you expect to get. And we compare the uniform sampler to Unigen, and you see statistically they're indistinguishable. So almost uniform is really very, very close to uniform. It's very good. But the key advantage that we have is scalability. So at the time we compared Unigen to XOR sample prime, which was the best of breed at the time. This was around 2015. And extra sample prime offer best effort for uniformity, did not offer any uniformity guarantee. And you see, an extra sample prime is a purple curve here. And I saw you here on different benchmark, and you see that Unigen, while it offers approximation guarantee, it offers its almost uniformity, it is still faster by several orders of magnitude from extra sample prime. So it was really significant progress. This progress was important that we started to tackle what was considered even a more difficult problem, which was model counting or constraint counting. Now you have an input formula and you want to count how many solutions does it have. This is called SharpSat. And SharpSat is complete for SharpP, which is a class of counting problem introduced by Valiant in 1979. Here a formula P or Q, you see that the only way it is not satisfied if both P and Q are false. So out of the 4 possible assignments, 1 is bad, so we have 3 satisfying assignments. Again, how do you scale it to large formulas? Again, this has a large number of applications. This is today, for example, probably the biggest application is in Bayesian inference, in probabilistic inference over graphical models, which we know can be reduced to SharpSat. But in reality, SharpSat is known to be a much harder problem than SAT. SAT, you can solve for millions of variables. SharpSat, you can solve for tens of thousands of variables. It's a much more difficult problem. So again, we offer approximate counting. And these ideas, again, they are not our idea, approximate counting. This was introduced by Stockmeyer first in 83. And he said, well, give me 2 parameters. One is the error tolerance, the accuracy, how close you want to be the correct count. And the other one is confidence. How confident do you have to be in the result? So he said we can have a randomized algorithm that with probability at least delta will give us a count that will be within factor of 1 plus epsilon for the correct count. The correct count is kappa. The algorithm will return count. And with high probability, this count will be fairly close to kappa. Again, the best algorithm developed for this was in Jerome Sinclair and Valiant in 1989, was in randomized BPP, randomized polynomial time, with an NP oracle. There was no implementation when we started looking into this, and it was clear why not, because it will have the same issues that we saw for sampling. It would not scale. It was a nice theoretical algorithm, but it has no chance of scaling to real life benchmarks. We realized our ideas can be extended to counting. Again, we use the M-random XOR clauses to partition the space into small cells. We select a cell at random. We count the number of solutions, multiply by 2 to the m. We get an estimate for how many solutions there are, and we iterate it. Each time we iterate it, we gain confidence. We have many such estimates. We take the median, and that gives us a pretty good estimate. And this method, of course, it's called SAT solving, so I can call it polynomial time, but relative to SAT oracle, this method is polynomial in the size of the formula in 1 over epsilon in 1 over log of 1 minus delta. And in comparison, in accuracy, again, we compare it to Cache, which was an exact solver. And we use the parameter we use is epsilon equal 0.75. But in reality, we saw that on problem that both solver can solve, we are within 5%. We are very close. We are 5%. We are very, very close to that. So that means that our tool perform better than the analysis. We need to improve the analysis of the tool. Runtime on small problems, Cache was faster. But if Cache does not finish in 5 minutes, it will never finish. And Cache is scaled to about 50,000 variables, and approximately scaled to hundreds of thousands of variables. So let me kind of start to wrap up. So first, I started with talk about neural nets, and it turned out that we can use these techniques to reason about neural nets. And one such work was done by Kuldeep Mill together with collaborator. He's now a faculty member at NUS, and they have looked at neural nets and they show how to use approximate counting for reasoning about neural nets. But let me finish with some philosophy. So one point I want to show you is that some people think of SAT as a hard problem, but we have had major progress in SAT solving over the past 25 years. In fact, I think one huge mistake was calling CDCL SAT solving. Who knows what the hell is CDCL SAT solving? You should call it deep solving. And then people realized that we made a huge progress in automated reasoning, analogous to the progress we made in machine learning. Once you have SAT solving, it's an enabler. You can solve many, many things. When you have a big hammer, go look for nails. Now, I don't want to say that we're done with scalability. In particular, my students, ex-students, Kuldeep, has continued to work on scalability for the past 10 years, and made, by now, I think he have like MC model count. We have approx MC4. It goes all the way to now, to version 4, and continue to improve on scalability. But if we step back, we see that we think that P versus NP is a central problem in computer science. And indeed, it is a very important theoretical question. But then all jokes say, what is different between theory and practice? In theory, they're not that different, but in practice, they're very different. So I would say P versus NP, beautiful theoretical question. In practice, it could see conceivable that P equal NP, but the polynomial is n to the 1,000, so it's completely impractical. Or it's conceivable that P is different than NP, but you can solve all of NP is n to the log n, which can be very practical if the constants are small. So there's no guarantee that solving P versus NP would yield practical benefits. Important to understand that. On the other hand, maybe NP-complete problems are not really hard in practice. So when I was a PhD student, NP-complete problems were scary. Now we solve them before we eat breakfast. And now it turns out we can create synthetic problems that are very difficult for SAT solvers. But real life problems are not that hard. Why? We don't have a good explanation. This is a fantastic theoretical question. If the role of complex theory is to tell us what is hard and what is easy, we need a theory will tell us why some SAT instances are hard and why some SAT instances are easy. And I'll finish by going back to my first question that I talked about, model-driven computer science or data-driven computer science. I don't think it's a paradigm shift. I would call it paradigm glide. We have the two paradigms. We should work with both of them. If you go look at the undergraduate curriculum in physics, they still start with mechanics, electromagnetism, and optics, because this is still classical physics is still very, very relevant. But we must bridge the gap between machine learning and logic to get human-centered AI. Thank you very much.
Thank you, Moshe, for that interesting talk. Is there any questions? Please go ahead.
Hello.
Yeah,
Good evening,
I can hear
Professor.
you.
Yeah. So, like, I have a follow-up question on the dynamic testing part when we were discussing. So, like, we noted that the state space is very large, yet we need to have a sense of the error on each of the point in the state space. So, something similar we need to do for our neural network training also, where the state space is very large and we need sense of error on each of the some points. So just I want some pointers or some thought on how these how the progress on the testing part or that paradigm can be somehow used for useful training in machine learning and that problem.
So I think this is the fruits of the tree are, I wouldn't call it low-hanging fruits because it will take some effort to get them. But I think there is a huge room for to get some insights from here, from logic into the core of machine learning. And a younger colleague of mine here, Anshumalu Srivastava here at Rice, have done work on actually using hashing to help in the training of machine learning. And he showed that what he shows is using his algorithm, you can move the training. You don't, instead of using GPUs, you can move them to CPUs, and you get significant improvement in runtime and also in energy consumption, which is very high for training machine learning model. So we have been talking about how to combine his hashing algorithm with our approach, and we have not been able to nail it yet, but I think it's a very promising research direction.
Okay, thank you, Professor.
But you should take a
Professor,
look at
you mentioned
you should take a look at the work of Anshu Mali about hashing and machine learning.
Professor, you mentioned that there might not be much significant practical applications of P versus NP. Why do you say that, or what are your views on that? One of the slides you mentioned.
Yeah, but I said that the supposed NP is in polynomial time. The reality is we think that polynomial time is feasible, but this is just an idealization. Suppose I give you an algorithm which is n to the 10. How big numbers can you solve it? You won't be able even to solve it for n equal 100. In fact, I had a master student that look at a problem. It's computing the permanent, and he compared computing permanent has a fully polynomial randomized approximation scheme, and he compared it to an exponential time algorithm. And the answer was that up to roughly n equal 100, the exponential algorithm is actually faster. The polynomial time algorithm will be faster for larger n's. But by the time you get to n equal 100, none of the approaches works. None of the approach can solve problem with 100 variables. So to say polynomial time means feasible is idealization. So in practice, large degree polynomials or large constants may not be feasible. And exponentials, if I give you c to the n, but for small c, this actually might be feasible for fairly large n, depending on how small c is. If I tell you 1.0001 to the n, yeah, it's exponential, eventually be a large number, but it will take a while. So we're making assumption in complexity theory. One, it's asymptotic, n goes to infinity. When in real life, n does not go to infinity. When I was a freshman student in physics, one of the TAs, who was a smart ass, asked us, what is the limit of log n when n goes to infinity? And we said, well, we're freshmen, we're not idiots, we know it's infinity. He said, you're wrong, it's 50. I said, 50, how did you get 50? He said, there's no number in the universe that if you take log, you get log was base 10, okay? There's no number in the universe, if you take log, it will be more than 50. Why? So 10 to the 10 to the 50. So that's bigger than anything that practical for us in the universe. Beyond that, for us, infinity could be 10 to the 10 to the 10 to the 50. So log is 50. So we make idealization complexity theory. And they're beautiful, so we get beautiful theory, but we should not forget these are idealizations. N does not go to infinity. And in reality, if you have a problem with maybe n cube, is still practical. Maybe n to the up above n cube, n to the fourth, it stopped being practical.
Right. Thank you.
Any other questions?
Yeah, Prof. One follow-up question, key. In all the work, like when you say this getting the work from this logic to the machine learning. So one very basic question that I think is like the domain and the space of these machine learning functions that the neural networks are trying to approximate are like Rn to R. So like the continuous valued function and the much of the functions or problems in the logic like the satisfiability or Boolean functions are discrete. So can like this be some kind of a hurdle or how the solutions in this discrete problem space, how easily it could be extended to continuous problem space. Any thoughts?
So yeah, first you have to remember that continuous is also an idealization. In reality, they work on floating point numbers. Now there is an extension to the work that we've done here, and this is the weighted version. In the weighted version, you take each variable and you assign a weight to take a variable p, you assign a weight to p being true, and you assign a different weight to p being false. And the weights are real or floating point number, real numbers, okay? But real, I mean real, that means floating point numbers. So now take each assignment. The weight of the assignment is the product of all the weights of each variable, right? In each assignment, each variable occurs positive or negatively. So you take the appropriate weight and you take the product of the weights. And this is the weight of the assignment. And now we can do, for example, weighted counting, in which you sum up all the weights of the satisfying assignments. And now you're really in a quantitative world. It's not just about counting. It's about really, this is really what people call kind of discrete integration. And so you are much, much closer now to the world of neural nets. I say it's about building bridges. And, you know, I mean, yes, you have real numbers there, but you have to remember at the end, a neuron fires or doesn't fire. And that value is Boolean, but the way you combine the neuron, that's where you have the weights. But again, the weights are not real numbers, they're floating point numbers, because that's what we can compute with. So there again, we have to push the logic to be more quantitative. So we've all grown up on logic as fully qualitative, just about true and false. And what we've been doing here for the last decade was try to make logic quantitative, so we get closer to the world of machine learning.
Yes, thanks, Professor.
Are there any other questions? So Moshe, I had one question about, like typically there's a lot of work trying to use neural networks for learning invariants for, programs, for, trying to prove correctness of programs, loop invariants. And, there's been recently, so one of the problems with neural networks is that you can't extract a logical formula from that which describes your invariant easily. And I think recently there have been some work on this, on trying to, what are these called? I think continuous logic networks, where you kind of use a fuzzy interpretation of Boolean values and SMT formulas also. And so, do you think that is a promising way to be able to use machine learning effectively in program verification?
So I think there is a growing realization that the method that was developed, as successful as it is over the past decade in machine learning, kind of just neural nets with different architectures, DNN, RNN, CNN, and all the different things. On one hand, they made tremendous progress, but people are realizing that there are inherent limitations. And this is now kind of the big question of the day. How do we go to the next level? And that's why there is some, IBM just held a couple of weeks ago, a week-long workshop on neurosymbolic reasoning, on neurosymbolic machine learning, because they believe that that's where the direction is to go, but integrating neural net and symbolic reasoning. How to do this integration? That's the $64 million question. And there are many, many different approaches proposed, tensor network, logic networks, I mean, all kind of way of integrating neural and symbolic reasoning. I think at this point, we have to let what we call a thousand flowers bloom, and see which one will ultimately provide that. Even basic questions about, there was proposal about what we call a tight integration. You put the logic inside the neural nets. And the proposal for loose integrations, you have several neural nets, and then you use above them a layer of symbolic layer to integrate the results from different boxes. So this is now a very active area, and I'm not very good at predicting the future. But I think we're seeing lots of activities, and ultimately what will work will get everybody's attention.
Thank you. Any other questions? Let's check the chat. Okay, I don't see any more questions on the chat. Okay, so if there are no more questions, let's thank Professor Vardi for taking the trouble to deliver his talk to us and interact with us. And we hope you will come personally once and visit Bangalore and IISc. Thank you, Moshe.
Namaste.